Training reinforcement learning agents has a strict speed limit, and it's us. Right now, the process relies on static, human-curated task suites to teach models how to act. But if the training environments themselves become a learnable output, that bottleneck disappears. The constraint shifts entirely from human labor to raw compute and pre-training data. A new framework called SPADE attempts to operationalize this exact shift for language agents. Instead of relying on a fixed pool of tasks, SPADE allows a single set of model weights to dynamically design its own training curriculum as it learns. Older approaches like paired tried to generate tasks using entirely separate adversary networks, but they rarely escaped simple grid world constraints. By making environment design a learnable component integrated directly into the training loop, SPADE lays out a concrete blueprint for continuous, open-ended self-improvement. The engine powering this framework is a single Qwen 3 30B mixture of experts model. The training recipe forces this model to play two distinct roles simultaneously: an environment designer and a reasoning agent. The designer writes complete, long-horizon training environments from scratch, outputting executable Python code using a standard GIM-style interface with reset and step functions. As the agent learns to navigate these generated worlds, both roles are continuously updated through a reinforcement learning algorithm called GRPO. The agent is rewarded for solving tasks, but the system needs a way to evaluate and reward the environment designer for making good ones. The solution is a metric called hint-based regret. The math is straightforward. Take the agent's performance on a task with privileged hints, minus its performance without hints. If it is solvable with hints but fails without them, the environment sits precisely at the edge of the agent's current ability. We've seen this with help minus without help trick before in Google's SEED framework to manufacture reward signals. SPADE takes that exact same mechanism and applies it one level higher to generate the task pool itself. This regret loop forces the designer to constantly chase the expanding frontier of the agent's capabilities, ensuring tasks are challenging but mathematically feasible. But you cannot just turn this system on and expect it to work. The ablation studies reveal that pure, ungrounded open-ended generation completely fails. To produce useful worlds, the designer must be explicitly grounded on documents sampled from massive pre-training corpuses, like DCLM or Megascience. The system also requires an accumulated memory buffer of past environments, annotated with exact regret scores and specific skill tags, to maintain its trajectory. The fact that ungrounded generation fails is a significant data point against the idealized narrative that AI can achieve pure self-improvement completely from scratch. If you find these hard engineering realities interesting, subscribe to the channel. We break down the actual mechanics of model training every week. For developers looking to implement this, there are severe hidden costs. The first is the sheer execution infrastructure required. Every generated environment is model-written Python containing state transitions and reward functions. You have to safely sandbox and run that untrusted code at massive RL rollout volumes. The second hidden cost is the vulnerability to miscode xerifiers. Because the regret filter selects for task difficulty rather than code correctness, the agent will easily learn to exploit broken reward functions. The SPADE recipe is public and uses open backbones, but standing it up requires a massive, unstated budget for secure execution pipelines and downstream failure detection. If you've heard of this paper, you've likely seen the headline metric circulating the community, a massive plus 13.9 gain on the ACEBench-Agent benchmark. This chart illustrates that metric, alongside a plus 5.7 lift on the BFCL v4 multi-turn benchmark, framing this as a dominant leap forward in agentic tool use. But look closely at the methodology. The baselines for these specific tool use numbers were not tested in-house. They were transcribed from other papers. Those transcribed baselines used completely different training data, different compute budgets, and different evaluation protocols. A cross-paper comparison under unmatched conditions cannot be treated as a controlled experiment. To find the rigorously tested numbers, we have to look at the game setting, where a fixed environment baseline called RLEV was tested fairly against SPADE on the exact same architecture. Under matched conditions, the true earned capability gain emerges. It is a plus 5.3 average improvement across 8 held-out math, science, and reasoning benchmarks. Pushing a 30 billion parameter model up 5.3 points on rigorous held-out benchmarks is an impressive achievement on its own. The plus 13.9 headline is a cross-paper artifact that distorts the framework's actual verified capability. There is also a deeper mechanical flaw buried in the framework's core reward signal, specifically in how it calculates the finite sample regret estimator. Mathematical regret is the gap between optimal performance and actual performance. By definition, true regret cannot be a negative number. Yet, when the authors ran this setup on smaller 4 billion and 8 billion parameter models, the math broke down. This graph plots the training progress, showing the finite sample regret estimate actually dipping below zero for long stretches of the run. This means the environment designer spends extended phases of training being steered by an estimator whose sign is flipped, pointing in the mathematically wrong direction. The paradox here is that despite this breakdown in the math, the method still works and the agents still improve. Does this mean the SPADE pipeline is just extremely robust to noisy reward signals? Or is there an unexplained confounding variable driving the learning behind the scenes? To settle the debate, researchers need to retrain those tool use baselines on the exact same Qwen3 backbones. We need to see if that plus 13.9 gap actually survives a matched test. We also need outside groups to test this self-play scaling trend on a non-Qwen architecture to prove these results aren't just an isolated anomaly of one model family. SPADE delivers a crucial proof of concept, showing that dynamic training environments can be learned on the fly. But the mathematics of its self-supervision are far from settled, leaving heavy open questions for the next generation of model training.